We created a full system prototype of Direct Machine Physical Memory Allocation Unit, or DMU for short, to restore precise memory allocation in hardware compressed memory. Instead of reusing the traditional page-based memory allocation, DMU uses a novel objective-based allocation, where the OS directly expresses the high-level objective of how much machine physical memory to allocate. To use DMU, we created a standalone kernel module named Machine Physical Memory Manager. The OS has booted up with 2 cores. Note that the OS boots up with 4 GB of physical memory. This is because hardware compressed memory allows the OS to use many times more physical memory than machine physical memory. Next, we use the manager to allocate machine physical memory to the jobs by specifying the total allocation objective for each job to DMU. We run 3 jobs. Each job is an identical instance of MCF running under its own control blocks. We allocate 70 megabytes, 100 megabytes, and 155 megabytes of machine physical memory to each control block, respectively. The jobs have just started running, so most of their allocated memory is not being used at the moment. Here we show how well DMU compresses and stores each job into its allocated memory. As you can see, Linux reports MCF1 uses 112 megabytes worth of physical pages. Out of these, 18 megabytes are not compressed. The rest are compressed so that MCF1 can stay within its 70 megabytes total allocation objective. MCF2 and MCF3 are not compressed. For example, Linux reports that MCF3 currently uses roughly 100 megabytes worth of physical pages. Since the total allocation objective for MCF3 is 155 megabytes, there is currently no need to compress. Here, we demonstrate how DMU assists OS with enforcing the total allocation objective for a job when hardware alone cannot. DMU raises the compressed memory fault, which is an interrupt, to report that MCF1 has used up all of its allocated machine physical memory. OS timely swaps out some data from MCF1 without pausing it. Because MCF1's values have been swapped out, the unused allocation of MCF1 is positive. MCF2 and MCF3 are not swapped out because they are allocated more machine physical memory than MCF1. We also demonstrate other objectives that OS can express to DMU. The minimum uncompressed cache objective is the minimum amount of recently accessed pages that should remain uncompressed. As you can see, the amount of uncompressed pages is more than this minimum uncompressed cache objective. The unused allocation objective allows the OS to control how much machine physical memory to free from individual jobs. Increasing the unused allocation objective of control block 3 to 50 megabytes causes DMU to schedule more compression for the job to free up 50 megabytes of memory from that job. DMU enables fast machine physical memory deallocation. Here, we deallocate 50 megabytes from control block 3 by reducing its total allocation objective down to 105 megabytes. Deallocation is fast because it only involves simple subtraction and addition operations on the control block fields. All deallocated memory is tracked collectively by control block 0. As you can see, objective 1 of control block 0 increases by 50 megabytes. Multiple programs can share the same control block. To run another program under control block 1, we increase the total allocation objective of control block 1. Then, we run a memory hog program under control block 1. Control block 1 is currently also being used for MCF1. Due to the hog program, Linux reports the system is using 3.6 gigabytes of physical memory, even though the FPGA board has only 1 gigabyte of DRAM. All programs have finished. The checksums match the checksum from an execution in a regular desktop. Thank you for watching this demo of our prototype of DMU. We will release the FPGA bitstream and the OS binary used in this demo as the first publicly available prototype of a hardware-compressed memory system. Please refer to the description section of this video for the link to the prototype files.